Pop culture has trained us to expect a very specific, spectacular death if we ever step out of an airlock without a spacesuit. We picture astronauts violently exploding or instantly flash freezing into solid blocks of ice. But human skin is surprisingly tough. Our blood vessels and tissues are strong enough to keep our internal organs safely contained in a vacuum. You won't pop. The actual mechanics of what happens to a human body in space are much stranger. The most obvious problem up there is a lack of oxygen. If that were the only issue, an astronaut could simply strap on a standard aviator's oxygen mask and walk out the door. To understand why a mask fails, we have to look at the invisible force pressing against you right now. At sea level, miles of atmospheric gases push down on every square inch of your skin. Our biology evolved entirely dependent on that continuous mechanical pressure. To survive outside our atmosphere, you must have a steady supply of breathable air, and you must physically replace the heavy, crushing weight of the sky. Down here on the surface, that heavy atmospheric pressure keeps the water inside our bodies in a stable, liquid phase. This chart tracks pressure as you climb. At 19 kilometers, atmospheric pressure drops to 6.3 kilopascals, 1/16th of sea level. Because boiling point depends on pressure, at 6.3 kilopascals, water boils at 37 degrees Celsius, normal human body temperature. This is the Armstrong limit. If you cross this line unprotected, any moisture exposed to the environment starts to rapidly boil. This extreme process is known as ebullition. The tears in your eyes, the protective fluid lining your lungs, and the saliva on your tongue instantly turn into vapor. Your skin maintains enough internal pressure to keep your cardiovascular blood in a liquid state. However, as water vaporizes and gases expand inside your tissues, your entire body swells to roughly twice its normal size. This extreme low pressure explains exactly why an oxygen mask fails. Even if a mask pumps 100% pure oxygen into your airway, there isn't enough external pressure for your lungs to physically push that gas into your bloodstream. Past the Armstrong limit, the human body ceases to function. Without oxygen entering the blood, the brain starves. The time you have left before blacking out, known as your time of useful consciousness, shrinks to between 9 and 15 seconds. We know what this looks like in reality because of a 1966 spacesuit test inside a massive NASA vacuum chamber in Houston. Technician Jim LeBlanc was inside, testing a pressurized suit in conditions simulating an altitude of 150,000 feet. During the test, a pressurization hose supplying air to his suit completely detached. In a split second, LeBlanc's body was exposed to a near-vacuum environment. As the pressure plummeted, he experienced the physics of the Armstrong limit firsthand. His final distinct memory was the sensation of the saliva boiling right off his tongue. Hypoxia set in immediately. He lost all useful consciousness and blacked out 15 seconds later. The team monitoring the test scrambled. They rapidly repressurized the chamber and reached LeBlanc in roughly 25 seconds, restoring his oxygen in a critical, fleeting window. He survived the ordeal with nothing more than a sore ear. This historical record is a testament to the quick response of the NASA crew. A survival time measured in seconds proves how vanishingly small the margin for error is when human biology meets a vacuum. A spacesuit operates as a sealed, heavily engineered, human-shaped pressure vessel. Its primary job is to artificially contain an atmosphere. Humans have zero capacity to adapt to the physical realities of the cosmos. The only way we survive leaving our planet is by packing a tiny wearable piece of Earth's atmosphere and taking it with us. Once the suit solves the pressure problem, it immediately has to deflect a second, equally lethal threat. Without Earth's atmosphere to filter the light, solar ultraviolet radiation hits objects in space with full force. During the Gemini 9 mission in 1966, astronaut Gene Cernan was working outside his spacecraft when a few layers of his suit's back seam tore. The brief exposure to intense solar heat left him with a severe, highly distinct triangular sunburn. To prevent blindness and severe burns to the face, modern space helmets are equipped with thick, UV-stabilized polycarbonate visors. The suit effectively acts as a personal, wearable ozone layer. The Onstrand line, at 19 kilometers above the surface, marks the exact boundary where our planet permanently stops doing the invisible work of holding our bodies together and shielding us from the sun. The universe is a staggeringly hostile place for biological life. We can only explore it by engineering, wearing, and carrying our own physics into the dark.